All right, so we're going to take a few minutes and talk about chemical formulas. And this is mostly going to be comfortable with you later because you're going to practice it a lot. But it is important that we give some definitions here. So first of all, molecular formulas, representations of molecules which consist of the following: chemical symbols and subscripts. How many of them are there, right? That's what a molecular formula is, H2O. So there are 2 parts of hydrogen for every 1 part of oxygen, right? Subscripts are used only when more than one atom of a given type is present, as in H2O. A structural formula gives the same information, but it also shows how they're connected. So a structural formula is going to show something like that for H2O. Okay? So here are some examples. Methane, here's the molecular formula of methane. And here's the structural formula of methane. Now, we know that these atoms are not like little H's, right? Or there's no little C in there for a carbon atom. It's really a ball, right? It's a bunch of electrons and protons and neutrons. Well, if you want to give more of a 3-dimensional representation of that, because chemistry is 3-dimensional, right? All of chemistry really is 3-dimensional. So sometimes it's good to think about the actual shape of this methane molecule. So if we want that, we might draw hydrogen atoms out as in little white spheres, right? You see those little white balls right there? And then carbon as a black ball in the middle, right? So this will give us sort of a 3-dimensional, like where's the hydrogen atom with respect to the carbon atoms, right? Or we might want to give something a little more realistic. And this is hard to see. So you can see why this would not be the best option for methane for all conversations, but sometimes you want to think about where the electrons actually are. And it turns out that molecules really do have high density of electrons all around. So this is called space filling, right? This is called ball and stick. You can see that from the reading down here, right? Ball and stick and space filling, and we use these to make different make different points, right, in different conversations. So let's talk about now elements and how we're going to see those. Now, a lot of elements consist as only individual atoms. For example, copper, cobalt, nickel. How do you spell nickel? Did I miss mine? Do that again. Nickel, right? Sodium, magnesium, right? Carbon. However, there are 7 diatomic molecules. In elemental hydrogen really shows up. Hydrogen in nature shows up as H2. Nitrogen shows up as N2. Oxygen shows up as O2, right? And by the way, those 7 show up on the periodic table like this, right? Where this is nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen's way over here, right? Lithium is here, right? But these 7 are the ones that show up as diatomic molecules. And what's right here? Neon. And what's right here? Helium, right? But it's these 7. Let me get a different color here. And if easy to remember if you think of them as in like a backwards, well, upside down L or a backwards gamma, and hydrogen's over here, right? So if you think of these things are all together, those are the ones that show up as diatomic molecules. Sulfur shows up as S8. And I'm going to have this on the slide here, but phosphorus shows up as P4. Right? So these are how these things show up in nature, and they're called their standard states. Here's an example of different representations of S8, sulfur, molecular or elemental sulfur. So a molecule of sulfur is composed of 8 sulfur atoms, so we might say that would be the molecular formula. Here's the structural formula. Here's the ball and stick formula. And here's the space filling formula, right? But these are all the same thing. So it just depends on what we're trying to communicate with the symbolism that we use. Now, let's look at hydrogen. If you see, if you're trying to draw 1 atom of hydrogen, you might draw it as like a little white ball. If you try to draw 2 atoms, you would write it as that, right? 2 atoms of hydrogen. If you said hydrogen molecule, you'd put the 2 down here, right? See it right there? And then you would draw it like that because there's a bond between the 2 hydrogens, right? And if you were doing 2 hydrogen molecules, can you see you'd have 4 atoms here? 1, 2, 3, 4, right? So there's 4 hydrogen atoms, but if you're trying to talk about 2 molecules, this is how you would write it, and this is how you would draw it. Okay? So you can see that this notation is going to be very descriptive, very important. Now let's talk about empirical formulas. Empirical formulas indicate the simplest whole number ratios of the atoms in the compound. For example, if benzene, the molecular formula of benzene is C6H6, but you see these are both multiples of 6, right? So if I divide everything by the lowest number here, then I'm going to get CH. So this is the empirical formula of benzene, and here's the molecular formula of benzene. Okay? Acetic acid, which is the important element of vinegar. Vinegar is about 3 to 5% acetic acid. It's mostly water, right? But vinegar has acetic acid in it, and its molecular formula is C2H4O2. Can you see that these are all multiples of 2? Right? So we divide everything by 2 to get its empirical formula. Right? We'll describe later why empirical formulas are valuable to us, but for now, just appreciate that that's what the empirical formula is. All right, so here's benzene. I mentioned benzene a minute ago. It's C6H6, C6H6. That's the molecular formula. Here's the structural formula. Here's the ball and stick formula. Here's the space filling formula. And here's a picture of benzene, right? It looks like water. Doesn't taste like water, though. Do not taste it. All right? I mentioned vinegar a second ago. Well, this is mostly water, right? It's about, let's say, 5% vinegar, 5% acetic acid, CH3CO2H, right? Oh, by the way, sometimes we do molecular formulas like this to indicate that we've got different pieces in it, right? So I could have said C2H4O2. That would be like the pure molecular formula. But sometimes we do something like that. We might call it a condensed structural formula. Can you see how this, let me get a different color here. When I do the CH3 like that, I'm giving the reader some hint about how these things are structured. There's my CH3, and can you see a CH3 inside this green circle down here? There's my CO2, right? That's what that is. And there's a hydrogen, which is in a different condition than all the other hydrogens, and that's why it's over here on its own. All right, so anyway, you can see there's many different ways to do this. Here's the ball and stick formula. They all represent the same thing, right? If we want the simplest version of it, we might do the empirical formula, which is CH2O. Or if we want to specify a little more, we might say the molecular formula. If we want to specify even more, we might give the condensed structural formula. If we want to give even more information, we might use the structural formula, right? These are all ways to draw these things, okay? Now, isomers is a term, we won't use this a whole lot this semester. This is really more in organic chemistry. It's possible sometimes to have different arrangements for different molecular formulas. Methylformate, so acetic acid looks like this. Here's the structural formula for acetic acid, right? I know because I draw this a lot. And methylformate looks like this. Now I'm getting a little bit lazy here. See, these have the same molecular formula. This is methylformate. They have the same number of atoms in them. They're both C2H4O2, but they're arranged differently, right? And those are called isomers, one of another. So this next picture, I just showed you that. All right, got a little ahead of myself. Where am I here? Just showed you that. Acetic acid, they've got exactly the same atoms in them, but they have very different properties, right? Because the atoms are arranged very differently. All right. And so here's some more examples. Molecules such as carvone or spatial isomers. Here's carvone plus, carvone minus, carvone, what is this positive? No, plus, yeah, plus shows up as in these kind of seeds, and carvone minus shows up in this plant here. And I don't think I want to say anything else about that. All right, so we talked in this section about representations of chemicals. And we use chemical formulas. We talked about molecular formulas. We talked about structural formulas. We talked about empirical formulas. And then models like ball and stick and space filling. And we also talked about isomers. All right, see you soon.